Okay, in this video we're going to be testing the claim about a mean when sigma is not known. Okay, in the last video we talked about how to test a claim about a population proportion. So here we'll be doing the same thing, but this time with a population mean. We want to test a claim about some population mean when sigma is not known. Now we won't do the one where sigma is known because it is very rare that we want to test a claim about some type of population mean when we already know the population standard deviation. Okay, so here we got a couple of requirements that we need to mention. In this case here, for you to test a claim about a mean, you must have a simple random sample. And what that means is this: each sample of size n has an equal chance of being selected. And then number two, either the population is a normally distributed population or the sample size is bigger than 30. Now this is pretty much the same as for the requirements when we were finding the confidence interval for a population mean, or estimating the population mean. Okay, now once those requirements are met, we can use the test statistic. And this is what the test statistic is. You got t is equal to x bar minus mu divided by s over the square root of n. In this case, this is going to be your t test statistic, which is t. X bar is your sample mean. The mu is going to be the population mean that comes from the null hypothesis. And then that's divided by s over the square root of n. S is the sample standard deviation that's going to be given, and n is the sample size. Okay, so that's going to be the test statistic formula that you'll use when testing your claim about a population mean. Okay, and also the table that you're going to be using is the same table that you use when you were doing the estimating a confidence interval estimate for a population mean. So here, this is your what we call table A-3, and for those of you who are watching this video and enrolled in my class, that's going to be table A-3, which is your t-distribution critical t-values. You know, you have your degrees of freedom on the left-hand side, and then we're going to use one of these two rows, either the area in one tail, and that's when you have a left tail or a right tail test, and the area in two tails, that's when you have a two-tail test. Okay, and those significance levels are listed. Okay, that's very important. All right, now the way now that table, I should mention, is for finding the critical values. Okay, now for the p-value, it will be best to use the TI-83 or 84 plus calculator. And in this case here, once you find your test statistic and the number of degrees of freedom, which is always going to be n minus 1, okay, that's the sample size minus 1, that will give you your degrees of freedom. We can find the p-value by using the TI-83 or 84 plus calculator. And the directions are, you press second and vars to get your distribution menu, then you select TCDF, and then that TCDF command will require that you use three items: the lower bound or the lower limit, and then your upper bound or upper limit, and then degrees of freedom. And this is the the way that you will do this. For a left tail test, your lower limit will be negative 999,999, and then your test statistic, and then the degrees of freedom. And then for the right tail test, your p-value will be this. After you select your TCDF command, your lower limit this time will be your test statistic, and then your upper limit is 999,999, and then degrees of freedom. But for a two-tailed test, it's going to be the smaller of the two results. Okay, if your test statistic is a negative, is less than 0, then you'll use this command. But then you're going to take twice the value that's obtained from that command. And the reason for that is this. Your p-value is split in half among two tails. Your alpha level is split in half among two tails. So that's why you take 2 times the value that you get from this command if it's less than 0. And then you'll use this one if your test statistic is greater than 0. Okay, and you'll see how this works out when I do some examples. Okay, now I do need to mention some of the important properties of a student t-distribution. In this case here, the student t-distribution is different from the different sample sizes. So as your sample sizes vary, that distribution differs, and it's based on the number of sample sizes that you have. Your t-distribution has the same general bell-shaped curve as the normal distribution. Its wider shape reflects the greater variability that is expected when S is used to estimate your population standard deviation, and S is your sample standard deviation. Number 3, the t-distribution has a mean of t is equal to 0. Number 4, the standard deviation of your student t-distribution varies with the sample size and is greater than 1, as opposed to the normal distribution where your standard deviation is going to be 1. And as your sample size gets bigger and bigger and bigger, then your student t-distribution gets closer to the standard normal distribution. Okay. Alright, now let's look at some examples of just this. Alright, the first example is just simply this. In statistics, what does DF denote? Well, in this case, DF denotes your degrees of freedom. So DF means degrees of freedom. Okay, now the next question. If a simple random sample of 16 speeds of cars on California Highway 405 is to be used to test a claim that the sample values are from a population with a mean greater than the posted speed limit of 65 miles per hour, what is the specific value of DF, which is your degrees of freedom? So in this case here, your degrees of freedom is always going to be n minus 1. That's the sample size minus 1. So n was 16, so it'll be 16 minus 1, which will be 15. So for this situation, you have 15 degrees of freedom. Alright, let's look at this second example. Assume that a simple random sample has been selected from a normally distributed population and test a given claim. Identify the null and alternative hypothesis, test statistic, p-value, critical value, and state the final conclusion that addresses the original claim. In a manual on how to have a #1 song, it is stated that the song must be no longer than 210 seconds. A simple random sample of 40 current hit songs results in a mean length of 238.6 seconds and a standard deviation of 56.03 seconds. Use a 0.05 significance level and the accompanying mini-tab display to test the claim that the sample is from a population of songs with a mean greater than 210 seconds. What do these results suggest about the advice given in the manual? Okay. Now, I realize that's a lot in this particular problem, but here, apply that 8 procedure that I talked about in the last 2 videos. So here is that hypothesis testing procedure from steps number 1 all the way to step number 8. So we'll apply that to these particular problems here. So if we look at this, let's look at step number 1. It's stating the original claim. So here the original claim was the fact that the sample is from a population of songs with a mean greater than 210. So the mean, we use the population mean, so that's going to be mu, and the symbol for greater than is this symbol, 210. So mu is greater than 210. That's step number 1. Step number 2 is stating the opposite of the original claim. Well, the opposite of greater than must be less than or equal to. So here, mu is less than or equal to 210. And from steps 1 and 2, step number 3 is writing our null and alternative hypothesis. Okay, so here the null and then alternative. Now the null always has an equal sign in it, so it has to be mu is equal to 210, and one of these will be the alternative. So here that mu is greater than 210 must be your alternative, because the alternative does not have equality in it. So the mu is greater than 210. And by the way, that mu is greater than 210, that's your claim. So I'm putting the word claim next to it. So your alternative hypothesis is the claim. And then step number 4 is your level of significance. Well, let's look back. Here we're using a 0.05 significance level that's given to us in the problem. So here, your alpha level is 0.05. Now step number 5 is your test statistic. That's your t-value. Well, if you look at your mini-tab display, you'll see this t right here represents your test statistic. In this case, it is 3.23. So here in step 5, we can just say that your test statistic is 3.23. And in this case here, if that wasn't given to us, we had to use that formula, that test statistic formula, to find out what it is. Okay? Now step number 6. Now step number 6 is a combination of both the p-value and the critical value, because in the directions it does say identify the p-value and the critical value. Well, I can help you with the p-value because it's given in the mini-tab display. That p represents your p-value. So here, the p-value here is 0.001. But we don't know what the critical value is. Okay. Now, what I'm going to do is draw a normal curve on the right side. Looking at your alternative hypothesis, which is mu is greater than 210, that tells me I have a right tail test. So here, this will be the shaded region that I'm talking about. That's going to be your critical region right here. Now, to find the critical value, that's where we use table A-3. Your degrees of freedom, in this case, they're 40 data values, so that's 40 minus 1, which is 39 degrees of freedom. And the alpha level is going to be 0.05 in one tail. The reason for that is because it is a right tail test. So it'll be 0.05 in one tail. And this is where we use this table, the t-distribution table. So in one tail, that's this top row, we find 0.05, and then we go all the way down to 39 degrees of freedom, which is right here. And 39 degrees of freedom with a 0.05 in one tail will be 1.685. So that means my critical value is 1.685. That's the critical value right here. So, step number 5, you have to do the p-value, which is already given in the display, and you have to use table A-3 or your t-distribution table to get your critical value using the degrees of freedom and your alpha level in one tail to get 1.685. Alright, step number 7 is my decision rule. And I'm going to do 2 decision rules since I have the p-value and the critical value. Now your p-value is this. If your p-value is less than alpha, you reject the null. And if I look at the p-value, that's 0.001, and my alpha level is 0.05, well, 0.001 is less than 0.05, so that fits our decision rule, so we can reject the null. Now, if you use the critical value approach, then notice that the shaded area is to the right of 1.685. That means it's got to be bigger than 1.685. So if our test statistic, which is your t, is greater than 1.685, you reject the null. And in this case, our test statistic, which is t, back in step number 5, is 3.23. You compare that with 1.685, that is bigger than, well, 3.23 is bigger than 1.685. So if you use the traditional method or the critical value approach, we reject the null. So here, you can use either one, the p-value approach, which is this one, or the critical value approach, which is this one. Now step number 8 is, right now, conclusion. Okay, so the conclusion is this. Now, we're rejecting the null, that means that we're supporting the claim. So that means that there is sufficient evidence to support the claim. That the sample is from a population of songs with a mean greater than 210 seconds. Okay. So there is sufficient evidence to support the claim that the sample is from a population of songs with a mean greater than 210 seconds. Now, what does the results suggest about the advice given in the manual? In this case here, the results suggest that the advice of writing a song that must be no longer than 210 seconds is not sound advice. Okay? Because there are songs out there that are longer than 210 seconds. So this will not be good advice. Okay, let's look at another example. And I'm going to apply that 8-step procedure that I did in the last example as well to this one. Assume that a simple random sample has been selected from a normally distributed population and test the given claim. Identify the null and alternative hypothesis, test statistic, p-value, critical value, and state the final conclusion that addresses the original claim. So in this case, a coin mint has a specification that a particular coin has a mean of 2.5 grams. A sample of 32 coins was collected. Those coins have a mean weight of 2.49575 grams and a standard deviation of 0.01451 grams. Use a 0.05 significance level to test the claim that this sample is from a population with a mean weight equal to 2.5 grams. Do the coins appear to conform to the specifications of the coin mint? Okay, so now here's where we apply the 8-step procedure. So here in step number 1, we need the original claim. Okay, and the original claim states that the sample is from a population with a mean weight equal to 2.5 grams. So mu equals 2.5. That's your original claim. And then step number 2 is the opposite of the original claim. Well, the opposite of equal to has to be not equal to. So mu is not equal to 2.5 represents the opposite of the original claim. And from that, we can come up with our null and alternative hypothesis. So step number 3, the null hypothesis has the equal sign in it, so the mu is equal to 2.5, and that right there is your original claim. The alternative hypothesis has the not equal to sign in it, so mu equals not equal to 2.5. Mu is not equal to 2.5. That's your alternative hypothesis. So there's your null and alternative. Step number 4, your alpha level of significance. In this case, we're using a 0.05 significance level that was given to us in the problem. So your alpha level will be 0.05. And then step number 5, is calculating the test statistic. Okay, now let's look at what's given to us in that sample. We had a sample of 32 coins, so N is 32. And those coins had a mean weight, so that's your X bar, of 2.49575 with a standard deviation of 0.01451. Okay, so those are your given values here in this particular problem. Okay, now this is where we use our test statistic, and that's T is equal to X bar minus mu divided by S over the square root of N. So your X bar was 2.49575 minus mu, which was 2.5. That came from the null hypothesis. by the way, divided by 0.01451 over the square root of n, which is 32. Okay. Now, when we type this in the calculator, you want to put your numerator in the parentheses and also your denominator in parentheses as well. Okay, so here's how we do this. Left parentheses 2.49575 minus 2.5, close parentheses, divided by, and then left parentheses 0.01451 divided by, and then second x squared for the square root, 32, and you might have to close the parentheses twice depending upon what type of calculator you have, and then hit enter. This will give you, to 3 decimal places, negative 1.657. So your test statistic here is negative 1.657. Okay, now, step number 6, you have to do both the p-value approach and the critical value approach. Because they ask for the test statistic, the p-value and the critical value. The p-value, it would be much easier to use your TI-83 or your 84 plus calculator and use that TCDF command. Okay. Now in this case here, take a look at your alternative hypothesis. It's not equal to, so that tells me that's going to be a two-tailed test. And according to this, since it's a two-tailed test, my test statistic is less than 0, so I'm going to do twice the value that's obtained from this command. That's this format. So what I'm going to do here is do TCDF and use negative 999, and then my test statistic was negative 1.657, and then my degrees of freedom, well, if n is 32, then my degrees of freedom must be n minus 1, or 32 minus 1, which is 31. 32 minus 1 is 31. Okay, so that's the format that I'm going to be using. Okay. But after I find out what that is, I'm going to take 2 times that value. So second and vars for your distribution menu. That's second and vars, and then hit your down arrow key to find TCDF. I just passed it. There it is. TCDF. And then you're going to enter that format. Negative 999,999, then comma, negative 1.657, comma, 31, close parentheses. Now, if you have the newer TI-84 Plus calculator, you know the lower limit will be this number, and then you'll hit enter. Then your upper limit will be your test statistic. Then you'll hit enter, and then you'll type in your degrees of freedom, and then hit enter. And then, now the 4 decimal places, that will be 0.0538. So this is 0.0538. But keep in mind, our alternative hypothesis was not equal to, so it's a two-tailed test. So when you find the p-value, that's going to be 2 times 0.0538 which would give you 0.1076. So the p-value here is 0.1076. Okay. Now, we also need the critical value approach. And that's when we use that t-distribution table. Okay. Now, degrees of freedom, we found that out to be 31. And your alpha level is 0.05. Now, we're using the 0.05 in two tails because not equal to tells me it's a two-tailed test. Okay? So now, we look at our table here. Find 0.05 in two tails. That's this right here. And then find 31 degrees of freedom in two tails. That's this value right here. 2.040. So that means my critical value, now since it's a two-tailed test, I have two critical values. Z is equal to negative 2.040 and Z equal positive 2.040. Okay. Now step number 7 is to make the decision whether to reject the null or fail to reject the null. I'm going to use the p-value approach because that's the one that is much easier to use than the critical value approach. Okay, so if you use the p-value approach, it's going to be this. If your p-value, your decision rule is this: if your p-value is less than or equal to alpha, reject the null. And my p-value is 0.1076. My alpha level was 0.05. If you compare those two, 0.1076 is greater than 0.05. So this does not fit our decision rule, so that means we fail to reject the null. Okay. Now, if you were to use the traditional method, then it might be much easier for you to draw the normal curve so you can see where your critical values are. Not equal to means it's a two-tailed test. So the area is going to be this critical region and this critical region here. And then you have negative 2.040 and a positive 2.040. So that means this: if your test statistic is less than negative 2.040, that's this area shaded to the left, or if the test statistic is to the right, meaning greater than 2.040, you reject the null. But in this case, your test statistic from step number 5 was negative 1.657. That's not to the left of negative 2.040, nor is it to the right of 2.040. So here we say negative 1.657 is greater than negative 2.040. We fail to reject the null. So you can see that you can use either one of these approaches. It's probably easier to use the p-value approach. So now, step number 8. Since we fail to reject the null hypothesis, then we have to say from the conclusion, and I'll bring this up, the null was your claim. We failed to reject the null, so that means that there is not sufficient evidence to reject the claim. So step number 8 is this. There is not sufficient evidence to reject the claim. That the sample is from a population with a mean weight equal to 2.5 grams. So that's your conclusion, using simple non-technical terms. And do the coins appear to conform to the specifications of the coin mint? And that answer is yes, and that's because the coins do not come from a population with a mean that's different from 2.5 grams. Okay, I'll do one more of these. And in this case here, we want to assume that a simple random sample has been selected from a normally distributed population and test a given claim. Identify the null and alternative hypothesis. Test statistic, p-value, critical values, and state the final conclusion that addresses the original claim. In this case, a simple random sample of 25 filtered 100 millimeter cigarettes is obtained, and the tar content of each cigarette is measured. The sample has a mean of 18.8 milligrams and a standard deviation of 3.49 milligrams. Use a 0.05 significance level to test the claim that the mean tar content of filtered 100 millimeter cigarettes is less than 21.1 milligrams, which is the mean for unfiltered king-size cigarettes. What do the results suggest, if any, about the effectiveness of filters? Okay, so in this case here, this is where we apply the 8-step procedure. So here, step number 1 is stating the original claim. And the original claims states that the mean tar content of filtered 100 millimeter cigarettes is less than 21.1. So that means that mu is less than 21.1. Okay, and then step number 2 is the opposite of the claim. Well, the opposite of less than must be greater than or equal to. So here we say that mu is greater than or equal to 21.1. So this is greater than or equal to 21.1. Okay, and then from steps 1 and 2, we can come up with our null and alternative hypothesis. The null always has the equal sign, so mu is equal to 21.1. The alternative is going to be one of these two, and it's always the one that does not have equality. So it would be mu is less than 21.1. And the claim is your alternative hypothesis. And then step number 4 is state the significance level. That's your alpha level, which is in this case 0.05. And then step number 5 is to calculate your test statistic. Okay. So in this case here, your test statistic, let's look at what we have. We have a simple random sample of 25 filtered 100 millimeter cigarettes. And that sample has a mean of 18.8 milligrams. So that's your X bar, 18.8. And your standard deviation is 3.49. So S is 3.49. That was given to us in the original problem that I read to you earlier. Okay. So now we can apply it, use our test statistic, which is T is equal to X bar minus mu, all that's divided by S over the square root of N. Your X bar is 18.8 minus mu from your null hypothesis is 21.1. All that's divided by 3.49 over the square root of 25. Okay, so here the numerator and denominator must be in parentheses in order for you to do this. So using our calculator, left parentheses in 18.8 minus 1.1, close parentheses, divided by, then left parentheses 3.49 divided by second x squared for the square root 25. And in my case, I have to close the parentheses twice. So my test statistic is negative 3.295, rounded to 3 decimal places. So here, negative 3.295 is my test statistic. Now in the problem, we need to find the p-value and the critical value. So we need to do both in step number 6. Now for the p-value, we use that TCDF command. Now my test statistic is less than 0. It's negative. So the command I'm going to be using is negative 99999 and then negative 3.295, and the degrees of freedom, N is 25, so my degrees of freedom is 24. And by the way, if you look at your alternative hypothesis is less than, so that's a left tail test. So in a left tail test, I do have to use this command and this format with the negative 6 nines and then your test statistic and then degrees of freedom. And my degrees of freedom, of course, is N minus 1, which is 25 minus 1, or 24. Okay, so now let's bring the calculator back up. Hit second and vars. Select TCDF. And then enter negative 999. Well, take that back. Second vars. TCDF. And then negative 999, comma, negative 3.295, comma, 24. Hit enter, and that's going to be 0.0015. Okay. It is a left tail test, so that means that's going to be your p-value right there, 0.0015. Now keep in mind you only do 2 times this number when you have a two-tail test. We have a left tail test, so that means the p-value is that number. We also need our critical value. Okay. The degrees of freedom is 24, and the alpha level from step number 4 is 0.05, and this is going to be in one tail because it is a left tail test. So the alpha level will be in one tail. So under alpha area in one tail, we find 0.05, which is right here. And there are 24 degrees of freedom, so we go down to 24, and we find that it's 1.711. And it is a left tail test, so that means that the critical value is negative 1.711. And that's the critical t-value here. It's negative because it's a left tail test. Okay. Now you could draw a normal curve you'll see that it is a left tail test, so the critical t-value has to be negative. Step number 7 is your decision rule. You can use the p-value approach or use the critical value approach. If you use the p-value approach, then that means this: if the p-value is less than or equal to alpha, you reject the null. If the p-value is less than alpha, you reject the null. Compare 0.0015 with your alpha level of 0.05. You can see that 0.0015 is less than 0.05, so we reject the null hypothesis. Okay, now for the traditional method, since our shaded area is to the left of the critical value, that means this: if your test statistic is less than your critical value of negative 1.711, you reject the null. And your test statistic from step number 5 was negative 3.295. And here negative 3.295 is less than negative 1.711. That's farther to the left. So reject the null. Okay. So now we can go ahead and write our conclusion, which is step number 8. So in this case here, we're rejecting the null, and the claim was the alternative. We reject the null, the claim was your alternative hypothesis. That means that there is sufficient evidence to support the claim. So our statement, our conclusion statement is this: there is sufficient evidence to support the claim that the mean tar content of filtered (100) millimeter cigarettes is less than 21.1 milligrams. Okay. And what does the results suggest, if any, about the effectiveness of the filters? It suggests that the filters are effective. Okay. Because if there's evidence to show, to support that claim, that the mean tar content in a filtered 100 millimeter cigarettes is less than 21.1 milligrams, then those filters had to be effective. Okay. So that would conclude this particular video on testing a claim about a population mean. So, good luck with the homework, and do email me if you have questions or concerns.